let's learn about the Pearson correlation coefficient. This coefficient is a measure for the linear correlation between two continuous variables. Now let's unpack this linear correlation. The first part is correlation. By now, we already encountered it a couple of times this lesson. The correlation is a measure for the link or the relation between two variables. We could have positive correlation, in which both variables rise and fall together, or we could have the opposite effect, negative correlation, where if one variable rises, the other one falls, and vice versa. Now remember that there is no causal connection going on here, not necessarily. It's just the observation of this pattern. Now the linear part in linear correlation basically indicates that this pattern of rising and falling together of these two variables, or the other way around, basically that this pattern is consistent throughout the entire dataset. Now in the course notes, I looked at a very concrete example, but let's here make it more general and look a bit more into detail about this linear part. Let's say that we have two datasets or two variables, x and y. X, for instance, could be the height of pet animals, and y could be the weight of the pet animals. So we have two variables and we want to see if there is a correlation or not. Now the linear part is that we could very easily get the value of y if we are given the value of x. To get from x to y, we simply multiply x with a specific number a, and then we add to this another number b. And by doing this, we simply get the value of y from the value of x. Now, if you remember from your algebra classes, then this equation that links these two values is the equation of a straight line. And that is exactly what the linear part in linear correlation means. It means that the relation between the two variables can be represented as a straight line. For instance, on this graph here, let's say that x is one variable and y is another variable. And thus we can see that if we go from x to y and we plot them all on the same graph, then we get a line. Now, of course, be very careful that this relation between x and y can be completely reverted. We could, for instance, revert this equation such that we can get the value for x if we have the value of y. Remember, correlation always goes both ways. Now, the Pearson correlation coefficient is a measure for how well our two variables follow this exact formula for a fixed a and b. In a sense, this coefficient quantifies how well all of these points lie on a line. Now, in this particular example, they exactly lie on the same line. So the Pearson correlation coefficient will be 1, but we will see many more examples and even generate them ourselves. Now, the mathematical formula for the Pearson correlation coefficient is given right here. Now, as is very typical for this course, we will not go into this formula. Instead, we will simulate data sets that give a very intuitive understanding for how this correlation works and how this number, the Pearson correlation coefficient, is linked to different data sets. Now, what is important here is that the Pearson correlation coefficient only works accurately if x and y, are two data sets that we're looking for correlation at, are normally distributed. However, by now we know that most of the data sets that we encounter are indeed normally distributed. However, it is always important that before you look at correlation between continuous variables, you first do your statistical tests, namely the Wilk-Shapiro test. So let's see how we can now visualize different levels of correlation between two variables using Python code. And the first step, of course, is that we need to generate two datasets or variables which are indeed correlated to one another, but for which we can fine-tune this correlation. Now, the first variable, which we will call x, will simply be a dataset that is distributed according to a normal distribution, with a mean being 0 and a standard deviation being 0.7. So how do we now generate another dataset or variable called y such that y and x are correlated to one another? Well, the first try could be to generate a y dataset by simply taking each value of our x dataset and multiplying it with a fixed number, a. Now a could be 1, 2, or even 3.14. In this way, we can abstract each value of y by just looking at the corresponding value in the x dataset. However, this also means that every value of our y dataset is 100% determined by the corresponding value in our x dataset, and thus these two variables are 100% correlated. Now, this is not exactly what we want, because, well, first of all, it is not a realistic situation of two 100% correlated variables, and the other thing is that at this point we still cannot tune our correlation. It's simply 100%. So how do we then generate y in a way that it is less correlated and that we can tune this correlation? Well, we can do so by adding noise. Now, this means that each value in our y dataset that we generate is still generated by multiplying the corresponding value in our x dataset with a fixed number, a, but now we add to each value a random number, which is called the noise. Now, this random number, this noise, is itself picked at random from a normal distribution. This normal distribution has a mean of 0 and a standard deviation noise param, which we can fine-tune. Now, because we add a random number each time we generate a new data point in our y dataset, the connection between x and y will be slightly different for each pair of data points. And therefore, the correlation will not be 100% anymore. We cannot determine the value of y by simply looking at the value of x, because we will always have this noise that is randomly distributed, so we don't know beforehand. Additionally, by making it such that we can determine this noise parameter that determines the spread of our noise, we can tune this correlation, this connection between x and y. For instance, if we increase the value of this noise parameter, that means that this number here that we add might have a larger spread, so it could be much lower or much larger than 0. This means, of course, that we will get much more noise and therefore less correlation. However, if we put this noise parameter to 0 or very, very small, then this noise will always be roughly 0, the mean of this normal distribution. Now, if this noise is roughly 0, then we are back to the previous case, where each element in our y dataset is simply the element in our x dataset multiplied by a fixed number, and thus 100% correlated. Now, implementing this in Python code, meaning generated y and x in this way, we obtain two datasets or variables that can be visualized in the following way. Now, what we see here is a scatter plot. So each point in this scatter plot, let's take this one for instance, has an x value associated with it, in this case a little less than -1, and a y value associated with it, in this case a little more than -2. So each data point has an x and a y value. And these x and y values, they come from these two correlated data sets. In this case, all of the points in this scatter plot are simply just forming one blob. There isn't really a pattern that we can see, and therefore we suspect that the correlation in this specific case will be roughly 0. There is no connection between x and y. Now, these histograms on both sides of the scatter plot are very interesting. Remember that each point here has an x and y coordinate. But these x and y coordinates are of course values of their corresponding data sets. Now, to see the data sets for x and y visually, we look at these histograms. So all of the y coordinates are collected and form the histogram of our y data set, which is the histogram that you see on the right. And correspondingly, all the x coordinates, if we collect them, form the data set called x. And you see this one on the top side here. Now remember, we generated x being a normal distribution. And that is exactly what we see here. Now, there is a very nice way to think about the connection between this scatter plot and their underlying histograms. Let's take, for instance, the y histogram. If we take all of these points on our scatter plot and we project them, so meaning just projecting them onto the y-axis, then we will get this histogram. So in the middle, there will be a lot of points corresponding to this bucket. Now, likewise, for the x values, if we take this scatter plot and we project it upwards to the x-axis, then all of these points will fall in one of the buckets of this histogram. and the more points that fall within a bucket, the larger the bar on this histogram. Now remember that these two parameters, this A parameter and the noise parameter, determine how Y is generated from X. And because we have these two parameters, we can change their values in order to generate a different Y from the same underlying X. And each time we will get a different correlation. Let's for instance increase this A parameter. Now when A is equal to 0, remember, then our X and our Y dataset are completely uncorrelated, because A was this fixed number in front of the X. Now if A is 0, then we multiply X with 0, and thus no information from our X dataset enters in the values of our Y dataset. Now if we increase A, then we see that this blob of scattered points will more or less get a direction. Now this direction means that there is a correlation between X and Y. Now what exactly does this mean in this case? We see that if X here on the horizontal axis is very low, so for instance -2, around -2, then the corresponding Y will also be quite low, also around this -2. Whereas X is large, around 1 and 2, then Y will also be between 1 and 2. And this is this relation, in this case a positive relation, because if X increases, then we see that Y increases, or vice versa, of course, because we're talking about correlation. If Y increases, then X also increases. And this is determined by this A parameter. However, because we have still a lot of noise, we see that not all of these points are on a very straight line. So then we can see what happens if we reduce this noise parameter. So if we reduce it, we see that all of these scattered points, they more and more follow a straight line. And if we make noise equal to 0, then we of course have our 100% correlation. Because if we look at our formula here, we generated Y, which is equal to A, which in this case is 1, multiplied by X plus 0, because our noise is 0. Now 1 multiplied by X plus 0 is simply X. So in this case, Y is equal to X, or X is equal to Y. And we can see this because these histograms, they are identical. And this shows that with the power of simulation and generating our own datasets, we can simulate various different scenarios, two datasets with an ever increasing level of correlation. Now, in the next lesson, we will actually see how we can implement these two datasets, or the generation of these two datasets, using Python code, and how we can generate these figures ourselves, such that you can play around with these parameters and build up an intuition about correlation between two continuous variables. So I will see you in the next lesson.